In 2012, a spacecraft the size of a small car crossed the edge of the solar system. It had been traveling for 35 years. No human-made object had ever gone that far. No instrument had ever sampled what exists beyond the heliopause, the invisible boundary where the sun's influence ends and true interstellar space begins. Scientists had models, decades of theoretical work predicting what Voyager 1 would find out there. The data came back wrong, not slightly wrong, not within acceptable margins. The magnetic field readings, the particle density measurements, the plasma environment, and none of it matched what the models said it should. And here's what that actually means. We didn't just discover something unexpected at the edge of the solar system. We discovered that our most fundamental assumptions about the boundary between our solar system and the universe were built on incomplete ground. Voyager 1 didn't confirm our understanding of the cosmos. It quietly dismantled it. Let's be precise about this. Voyager 1 launched on September 5, 1977. Its original mission was straightforward: a grand tour of the outer planets. Jupiter, Saturn, their moons, a close flyby of Titan. Scientific instruments, carefully calibrated, measuring what no probe had measured before. It wasn't designed to reach interstellar space, but the trajectory was right. The velocity was sufficient. And after the planetary encounters ended, mission controllers made a decision: keep it going, point it outward, keep the instruments alive, see what's out there. For 35 years, Voyager 1 traveled in a direction that has no name most people would recognize. Northward out of the ecliptic plane, away from the solar system's disk, into the region physicists called the heliosheath. Every year it moved farther. Every year the signal took longer to arrive. By 2004, the signal delay was 13 hours. By 2012, it was 17. The spacecraft was moving at roughly 38,000 miles per hour. In cosmic terms, that is almost nothing. The nearest star is 70,000 years away at that speed. But it was enough. The heliopause had been theorized for decades. The concept is straightforward in principle. The sun constantly emits a stream of charged particles, or the solar wind. That wind expands outward in all directions, creating a vast bubble of solar influence called the heliosphere. At some point, the solar wind slows, stalls, and eventually stops, overwhelmed by the pressure of the interstellar medium pressing in from outside. That boundary is the heliopause. Beyond it, true interstellar space, the space between stars, the medium through which galaxies move. Physicists expected a relatively clean transition, a measurable drop in solar wind particles, an increase in galactic cosmic rays, high energy particles from distant supernovae and other violent events across the galaxy, a shift in the magnetic field orientation, from one aligned with the sun's field to one aligned with the interstellar field. The models were specific. The predictions were confident. And then something happened. In August 2012, the charged particle data from Voyager 1 changed dramatically. Solar wind particles, or the ones originating from our sun, had dropped to nearly zero in under 3 days. Simultaneously, galactic cosmic ray counts spiked sharply. Mission scientists reviewed the data carefully. Then they reviewed it again. By most measurements, Voyager 1 appeared to have crossed the heliopause. But here's the problem. The magnetic field didn't change direction. This is the detail that doesn't make headlines. This is the part of the Voyager story that gets glossed over in the anniversary articles and the congratulatory press releases. The magnetic field was supposed to shift. Every model of the heliopause, every serious theoretical framework built over decades, predicted that once a spacecraft crossed into interstellar space, it would encounter a magnetic field with a fundamentally different orientation. The sun has its own magnetic field embedded in the solar wind. The interstellar medium has a different field, shaped by forces operating on galactic scales. The transition between them should be detectable, should be obvious. Voyager 1 crossed the boundary in August 2012. The magnetic field barely changed. For months, mission scientists argued about what this meant. Some suggested Voyager hadn't actually crossed the heliopause yet, that the particle data was misleading. Others proposed that the transition region was more complex than the models assumed. Then, in 2013, NASA formally announced that Voyager 1 had entered interstellar space. But the magnetic field problem didn't go away. It was quietly reclassified, absorbed into phrases like more complex than expected, and requiring further study. Let's be precise about this. When your model makes a specific, falsifiable prediction, and the data contradicts that prediction, the model is wrong, not incomplete, not approximately right, wrong in a way that requires explanation. The explanation has not been fully resolved. There's a second anomaly. In the years before the crossing, Voyager 1 passed through a region called the heliosheath, the turbulent zone between the termination shock and the heliopause itself. This region had also been modeled extensively. Solar wind particles slow dramatically here. The magnetic field becomes compressed and chaotic, and the environment becomes increasingly influenced by the interstellar medium pressing inward. What the models did not predict was the foam. In 2011, data from Voyager 1 revealed that the heliosheath was not a smooth, gradually transitioning medium. It was filled with magnetic bubbles, structures roughly 100 million miles across, formed by the tangling and reconnecting of magnetic field lines in ways that had never been anticipated. The heliosphere's edge wasn't a clean barrier. It was a churning, dynamic, structurally complex boundary that bore almost no resemblance to the theoretical models. And here's what that actually means. The models we use to understand the heliosphere, the very bubble that protects this solar system from the full intensity of galactic, cosmic radiation, were built on assumptions that turned out to be structurally incorrect. We are inside something we don't fully understand. The boundary of our solar system behaves in ways our best theories failed to predict. And Voyager 1 is the only instrument we have ever placed on the other side of it. Consider what Voyager 1 actually is. The spacecraft weighs 722 kilograms. It runs on 3 radioisotope thermoelectric generators, nuclear batteries, slowly decaying, producing less power every year. By 2025, several of its instruments will need to be shut down to conserve energy. By 2030, the power output will be insufficient to operate any scientific instruments at all. The signal it sends back travels at the speed of light and still takes over 22 hours to arrive. Humanity's most distant emissary, the only object we have ever placed in interstellar space, was running out of power, operating with instruments designed in the 1970s, and returning data that our most sophisticated models cannot fully explain. We have one data point, one spacecraft, one trajectory, one narrow corridor of measurement through the most complex boundary in our immediate cosmic neighborhood. Everything we think we know about the heliopause, about the interaction between our solar system and the interstellar medium, about the structure of the very boundary that defines the limits of solar influence, all of it rests on data from a single vehicle moving in a single direction. And that data surprised us. There is something deeper here, something the press releases don't address. The heliosphere is not merely an interesting scientific structure. It is a shield. The interstellar medium is filled with galactic, cosmic rays, high-energy particles, produced by supernovae explosions, pulsar winds, and other violent events distributed throughout the galaxy. These particles are dangerous to biological systems at sufficient exposure levels. They ionize molecules, damage DNA, disrupt cellular repair mechanisms. Earth's atmosphere provides some protection. The planet's magnetic field provides more. But the first line of defense, the boundary that deflects and attenuates the most energetic incoming particles before they even reach the inner solar system, is the heliosphere itself. Its structure matters. The magnetic bubbles in the heliosheath were unexpected. The behavior of the magnetic field at the heliopause was unexpected. The geometry of the boundary, the dynamics of the transition region, the precise mechanism by which the solar wind and interstellar medium interact, all of it is more complex, more variable, and less understood than the models assumed. We do not know, with precision, how effective our shield is. We do not know how it varies over the sun's activity cycle. We do not know how it has changed over geological time, as the sun moved through different regions of the galaxy. Regions with different interstellar medium densities and compositions. We know that the heliosphere changes. We do not fully know what those changes mean for what reaches us. Here's what that actually means. In 1977, we launched a spacecraft into the outer solar system, with no realistic expectation that they would survive long enough to reach interstellar space. They were designed for a 4-year mission. They are still operating, and the data they returned, particularly from Voyager 1, has not validated our models of the solar system's edge. It has complicated them. In some cases, it has contradicted them. The anomalies are real. The magnetic field behavior at the heliopause remains incompletely explained. The magnetic bubble structure of the heliosheath was not predicted. The precise location and nature of the crossing itself was contested within the scientific community for years. These are not small discrepancies. They are structural. They suggest that the theoretical framework we use to understand the largest scale structure of our immediate cosmic environment, a framework built over decades, refined with increasingly sophisticated instruments, tested against the best data available, is missing something. We do not know what that something is. Voyager 1 is currently more than 23 billion kilometers from the Sun. It is moving through a region no instrument has ever sampled before. It is returning data at 160 bits per second, slower than a 1980s dial-up modem, across a distance so vast that the signal takes nearly a day to arrive, and it is still finding things that don't match the predictions. In 2023, the spacecraft began transmitting corrupted data from one of its flight data system computers, a chip that had likely been struck by a cosmic ray, corrupting a small section of memory. Engineers at JPL, working with 40-year-old documentation and a communication delay of over 22 hours each way, diagnosed the problem remotely and rerouted the system around the damaged memory. The spacecraft recovered. It continued transmitting. It is still out there, still moving, still measuring a universe that keeps returning data we didn't quite anticipate. There is a version of this story that is triumphant. A spacecraft launched nearly 50 years ago, still operational, crossing a boundary no human object had ever crossed, returning the first direct measurements of interstellar space. That version is true, but there is another version, a version in which the only instrument we have ever placed beyond the solar system revealed that our models of the solar system's boundary were wrong in fundamental ways. A version in which we have one data point, one trajectory, one direction, one aging spacecraft to understand a structure that spans hundreds of astronomical units in every direction. A version in which the shield we live inside is more complex than we understood, and we have no plan to send anything else to study it. Voyager 1 will go silent in a few years. After that, there will be nothing out there to tell us what the edge of our solar system actually looks like. Nothing measuring it, nothing listening, just the boundary itself, doing whatever it does. Understood only as well as a single aging probe allowed us to understand it before the signal finally stopped.